Okay, take three, blahs or not, I'm going to keep going. Goals for today, we're going to be looking at comparing more than two means. We're moving away from paired data, looking specifically, at this point we've looked at one mean, we've compared two means, but what if we have more than two means that we want to compare data between? So we're going to look at this through a study with diet and weight loss. Researchers had recruited 160 overweight or obese subjects and randomly assigned them to one of four popular diet plans. Notice right there, that should be something hopefully you noticed right there. They randomly assigned them. That's important. We'll come back to that. Atkins, Ornish, Weight Watchers, and Zone, and there were 40 subjects per diet. Each subject's weight loss in kilograms from the beginning of the study to 1 year of being on the diet was measured. The data for the 93 subjects who actually completed the year-long study are available in Diets 2. So out of the 160 who began, only 93 made it through. So the research question, though, that we're interested in isn't, well, how many people stick with the diet? It's, do the diet plans differ with regard to how much weight people lose on these different diet plans? So it's not whether they stick with it, it's how much they lose. All right, so that's something to keep in mind as we go along. So I filled in the beginning. You may want to cover the answers and make sure you can do this part yourself. Observational unit hopefully is clear. Explanatory variable, which diet plan, and there are four of them. Categorical, response variable, amount of weight lost in a year on whichever plan they're on, and that's quantitative. Is it an observational study or randomized experiment? Randomized experiment, hopefully you can see why. They were randomly assigned. Okay, so there's random assignment, which leads to a randomized experiment. Describe the parameters of interest and assign symbols to them. This is where it gets a little bit more complicated than what we've done in the past. So far we've looked at two parameters of interest, but now we're going to look at more. So I'm going to use the obvious A for Atkins, O for Ornish, WW for Weight Watchers, and Z for Zone for my subscripts. So let's start with, what are we looking at? Parameters of interest. Is it going to be pi? Are we looking at proportion? Or are we looking at means, population means, mu? And hopefully you saw it right away, mu. Mu, and I'm going to start with Atkins. And this is the long-term or the long run average weight loss experienced by people on Atkins. Just to show you a slightly different way, we generally would want to be consistent with how we write these, but I want to show you a slightly different way. Let's do mu sub Ornish. So I would write these all the same, but instead of long run average, another way that we can write them is in general. Either of these is perfectly appropriate. So in general, the average weight loss on Ornish. So long run average or in general, both perfectly acceptable ways to do this. Now, we know we are going to have a mu for Weight Watchers and a mu for the Zone. You notice I always put generally put a line through my Z. It's in mathematics, we do that quite a bit so that we don't accidentally confuse it with a 2. So I'm not going to rewrite this whole thing, but they're all the same. And this is for Weight Watchers and this is for Zone diet. Now, the hypothesis. This is where it gets it feels different. Let's start with the null. The null is kind of nice. It doesn't really change. Sorry, that should be a comma, excuse me, and then a colon. What are we thinking for our null? Nothing special is happening with any of these diet plans. So will the weight loss differ? What do you think? Hopefully you said no. Nothing special is happening. So mu sub A is the same as mu sub O is the same as mu sub WW is the same as mu sub Z. So the diet plans do not differ with regard to weight loss. Try that again, weight loss on average. Okay, so they're not different. The alternate hypothesis. This is a little bit different. What we want to say, we're not going to write it out in symbols, all right? This is where let me say, what we're interested in is looking at, going back to that research question up here, do the diet plans differ? Does that mean that it's looking that every single one is different? No, all right? It's just wondering if any of them are different. So in this one, we're not going to write it in symbols. We're just going to say, at least, I will do it with symbols, at least one mu is different. So that's as far as we're going to go with symbols. And we'll talk more about that in a moment. And in words, at least one diet plan is different. Now, when we looked back at that research question, it did not say, do they all differ from each other? Remember, that is not what it said. It just says, do they differ? Now, that's not saying that each one's different from the others, just is one of them, any of them, different? All right, so my alternate hypothesis is at least one mu is different, and that's it. All right, not a good way, there's not a good way to write it in symbols. Please note that this does not mean you do not, this is absolutely not what you want to write. Where they're all different from each other, that is extremely restrictive, all right? This is very, very restrictive. This would be a very, very specific study. It would be worded entirely different. We're just asking, are they different? Is there a difference? So going back up, do the diet plans differ with regard to how much weight loss? It's not saying, is each plan different from every other plan, from the other plans that we're studying? That would be, and I'm just using my hands a lot there, I just realized, it would be worded much more restrictively. This is just saying in general, is there some difference? Okay, so you do not want to do this. This is no bad. Okay, so there's data. Like I said, it's in the diets too. I think I posted that. But the dot plots and summary data for each of them. And you can see the Weight Watchers one came out looking weird, but we've got Weight Watchers at the top in blue, Ornish in green, Zone in red, and Atkins in black. And weight loss, and these are in kilograms. So it's kind of nice to have the units, but the way these pop up, it doesn't. So what we do have are summary statistics. And so when we did up these dot plots, we copied this data in, obviously, and did up the dot plots. We have a sample size for each. Now, N, you're going to notice that it totals 93, not 40 each, because we're just doing the ones that people could actually they stuck with. There's the mean reported for each of them and each of their standard deviations. So looking, does one group appear to have a higher average weight loss, and which group is it? Ignoring the summary statistics for a moment, which one appears to have a higher, would you say, weight loss? I would say Ornish, and the reason I would say that is because they have these outliers out here where people lost a good amount of weight. So if I look down at the means, we'll notice that Ornish actually has the highest, 6.56 kilograms. So in this case, Ornish, yes, Ornish. And we can see it by looking at the dot plot, and we also can see it by looking at the summary statistics. Does one group appear to have higher variability in weight loss? Which group? And how are you deciding? Variability, remember, is how spread out they are. And in this case, if I'm looking at it, I'd say yes right away. And which one looks most spread out to you? Hopefully, once again, you're going to say Ornish. Because look at the spread here. It goes from here all the way over. I mean, so this is a pretty wide swath that it does. Let's see if that bears out with the numbers. Yes, it actually has also the highest standard deviation. So suggest some ways to quantify the observed difference in weight loss between the 4 diet plans. Well, okay, let's think about this. When we're comparing just 2 plans, or if we were just comparing 2, it would be easy. I would personally just take the difference in the means, right? Take the difference in the statistics and say, okay, well, let's see if that's meaningful, if it's a meaningful difference. But we have 4, and so we need to look at things in different ways. So we need to look different ways than when just 2. When there's just 2 groups that we are comparing between, it's easy. We've done that many times, but now we've got a lot more. We have 4. So it can be calculated several different ways. All right. So the first one is the observed max average minus the min average. All right. So ignore what's happening in the middle, but look at the extremes. So the highest mean we said was Ornish. And these are looking at means. What about the lowest weight loss? Well, that would be Atkins over the year. And this is the mean, and this is for Ornish, and this is for Atkins. And that difference is 2.64. So this ignores the middle. Okay, so we ignore the middle values on that one. So that's one way that we could do it. Observed max average minus the min average. Another way, or a different way we could do it, is with observed mean absolute difference. Now, you're going to notice absolute difference. Why is that important? When we look at the differences between, so we're actually combining all of the different ones. So 4.88, let's start, before we go any further, this is the zone, because that's 4.88, minus the difference to 4.59, which is Weight Watchers. And each of these, so then I'm going to do zone minus, you're going to do it, you want to make sure that you grab all the pairs, all right? And there are going to be 6 pairings possible for the difference. So this would be zone minus, let's see, Atkins. So we took care of all of the combinations with zone, right? So we're done with that. Then I'm going to take Weight Watchers minus, in this case, Ornish, and Weight Watchers minus Atkins. So that took care of all of the Weight Watchers ones. And then the only combination that we have left is Ornish minus Atkins. So a little bit time consuming to compute by hand. Why are we looking at the absolute values? Well, we're looking at the absolute values because we want to see, we don't want to be, if we just added these up, and let's say that the first one was -1 and the second one was +1. Well, you add those 2 together and it looks like, well, you've got no difference, 0. But in reality, there is a difference between the 2. So that's why we want to take the absolute value. So with the absolute value, we're looking at how big is the difference. Okay, so we're not worried whether one is specifically larger than the other. We're looking at what is how far apart are they? All right, and then we divide by the total number of groupings that we have, in this case 6, and we end up with a statistic of 1.369. Or there's something called the F statistic. And this is where we're not going to have to calculate this, don't worry. You're going to get this out of the applet. How much the means for each diet vary divided by how much people on the same diet vary. All right, this shows it talks more about variability diet to diet or person to person. That's what we're looking at when we're looking within this. So we're looking for the variability diet to diet and or person to person. All right, so that's a little bit different. So then how much the means vary, and then within the same diet, how much weight do people lose within the diet. So this won't be given to us. Or is there more variability diet to diet? So that's on top here, or person to person. And that's numerator and denominator. But the key question is, if there were no differences between the 4 diet plans with regard to how much people lose on these different diet plans, how surprising would it be to see? Now, we have to choose one of those to look at. We're going to look at, in this case, the max min. That's the one we're going to look at. And the max min value was 2.64 kilograms. All right. And this can be measured with the p-value. So we need to create the null distribution for values of what could have been by the null distribution alone. And we're going to do this from max minus min. That's the one we want to look at. And here's, I apologize, just going up a little bit. I forgot, at least is, so we could use number 1, 2, or 3. Like I said, we're going to use the max minus min. So we're going to look at number 1. And so this is looking if the null is true, just like we've done before with when we compared data, or when we did it with looking between 2 means. So we could do a tactile simulation using cards, like we did for comparing 2 groups with a quantitative response. Think a little bit how you would do that. First of all, how many cards would you need? Hopefully you said 93. Because we're going to need 1 for each participant, right? So we're going to need 1 card for each participant. And you're like, well, what about the 160? Remember, we're not using the 160 at this point because only 93 made it through. All right, so we're looking at the end result, 93. We're going to write the weight loss for each person on each card. So each person gets a card with their weight loss on it. Now, we're going to shuffle and deal into 4 piles. All right, now this is where you have to be a little bit careful. So there are going to be 4 piles. 1, 2, 3, 4. There's going to be a pile for Atkins, a pile for Ornish, Weight Watchers, and Zone. But how many are we going to put in each? And this is where going back to the sample data is going to tell us. We're going to use the counts because it told us exactly there were 26 people in Weight Watchers, 20 in Zone, Ornish, 26 in Zone, and 21 in Atkins. So that's the numbers that we want to deal out. Because remember, we're trying to figure out if these just all happen randomly, just by chance alone, what would happen. So then we would do this. Shuffle them all in, compute the average weight loss for each of these, and then record the max minus min average for the shuffled data. All right, so that's going to take a lot of time, right? So you're going to have to first calculate the average for the 21 and the average for the 20 for Ornish, the average for the 26 for zone, Weight Watchers, and the average for 26 for zone, figure out which is the largest, which is the smallest, take the difference. That is one data point, okay? On the dot plot, that's just one to generate that null distribution. So we need to repeat 3 and 4 many times to generate that null distribution and calculate. Then at the end, we're going to calculate the proportion of times that the max and min is greater than or equal to 2.64. Because remember, that was, we're looking at that max minus min statistic. So in the shuffle data, that would take a horrific amount of time, right? So what we really want to use is go into the applets. So we're going to once again use the randomization test for quantitative response applet to generate the null distribution for these. So we're first of all going to do it for max minus min. Now, take a peek at this and see if anything feels a little bit odd. Over time, we've gotten very used to the null being centered at 0. Now, this is not centered at 0. In fact, this null distribution is centered at 3. Does it make sense that the graph doesn't center at 0? And why are there no negative values? Well, remember, we're doing max minus min. And the max is always going to be greater than or equal to the min. There are not going to be negative values here. So it can't be less than 0. Max, in this case, is always going to be greater than or equal to the min. So we can't, the center can't be 0. All right, so it's always going to be shifted over. Because negative values in this case are just not possible. Comment on the shape of the null distribution. Could you have anticipated this? Well, yes, there are going to be, it's skewed right. And what do you, and you're like, well, what, there's some observations out here. It's pretty spread out, but the max can be pretty large, all right? The max weight loss could be, in theory, very large. So that's one thing that can happen. So we're skewed right. We are bound on this end by 0, but there are more that can happen at the upper end. So it does make sense that if it was going to be skewed one way or another, it's most likely to be skewed right. Indicate the region on the graph that depicts the p-value. Do you expect that evidence, do you expect to find evidence that type of dieting affects weight loss? Well, what was our statistic that we were looking at? Hopefully you remember 2.64. So that's probably like right about here. Let's call that 2.64. Remember, we're looking to see, oh, that's where my p-value would be. That's looking pretty large, wouldn't you say? Seems like the p-value will be very large. Or pretty large, you could say either one. They're going to be large. So we don't expect to find evidence that the type of diet actually affects your weight loss. All right, so looking at it there, it's not looking good. So that was using max-min. We can also use the same randomization test for quantitative response. You're going to notice you're going to go to the left-hand side of the screen, I believe it is, and you can choose which of these tests you want to use. And what about the mean absolute difference? So that was number 2 that we used. Does it make sense that once again the graph doesn't center at 0? Why no negative values? Well, remember before, it's the same ideas as before. 0 is the smallest that the mean absolute difference, I'm going to call this MAD, seems good, that MAD, so to save writing, MAD values can be. Because remember, we're taking the absolute value. All right, absolute values are always 0 or bigger, right? So the center of the graph will be somewhere positive. All right, could we anticipate the shape? Once again, yeah, it's skewed to the right a bit. We see some values out there. The mean in this case is 1.653. So we could, there's no limit. It's really how large the differences could be, but there is a limit to how small, because remember the absolute smallest they can be, because the absolute value that we're adding together is 0. So I would expect it to be skewed right if it's when it's skewed, because there's no limit on how large it can be. Once again, indicate the region, indicate the region of the graph that depicts the p-value. Do you expect to find the evidence that type of dieting affects weight loss? Well, we already see that we can see by just looking over 50% of the reps, the repetitions with the shuffled mean absolute difference as big or bigger than 1.369. So no evidence. That type of diet affects weight loss. And looking at this here, we can see, okay, remember, and you're like, well, where are you, how are you telling? Go back up here, and we calculate the mean absolute difference to be 1.369, right? So we go down here to this graph, and I look at the mean, the center is at 1.653. I'm looking at 1.369. That is definitely over 50%, given that the center is at 1.653. This is the mean, and this is the statistic we're looking at. All right, so we calculated that before. You notice we're using different numbers as we calculate these different statistics, but the same, we're getting effectively the same result. So what else do we have? Finally, we have using, once again, we can choose, same place, that F statistic. It's similar to the other two. Because 0 is the smallest that F values can be, the center of the graph will be somewhere positive. All right, so we already know that the distribution is skewed to the right because the least the F can be is 0. However, there's no limit to how large it can be. So we see their values out here. Indicate the region of the graph that depicts the B value. Do you expect to find evidence that the type of diet affects weight loss? So scan back up and see what we got for an F value. So coming up, and up here, I hadn't written it down yet. When I had run the applet, I got the F value as 0.54. All right, so if you can go back up and record that, that was the value that I got from the applet using the observed F statistic. So popped out for me. So if I scan back, go back down to where we were here, my value, so the mean is 1. My F statistic was 0.54. So 0.54 is what I got from my F statistic. That's like right here. This whole thing would be my p-value. So over 50% of the repetitions with a shuffled F are as big or bigger than 0.54. So the p-value is going to be greater than 0.50. So once again, no evidence that the type of diet affects weight loss. So effectively what we've been saying all the way along. So do the 3 tests back each other up? Yeah, they do, and that makes sense, all right? So it's just different ways of looking at the same data. Can we ever use the normal approximation? So at this point, we've been using simulation. Can we use the normal approximation? Yes. When comparing many means, the normal approximation, that is the bell curve, is a valid approach to find a p-value to test a hypothesis or a confidence interval only when the sample sizes are large enough. A loose rule is the samples are at least 20. If it's skewed, you want to obviously be bigger. Or the the samples come from populations that are normally distributed. Now this is a big and here. The standard deviations of the samples are approximately equal to each other. The largest standard deviation cannot be more than twice the value of the smallest standard deviation. So the normal approximation-based test is called the analysis of variance or the F-test. And this is a method of finding the p-value to test whether the data provide evidence against a null hypothesis that relies on the F statistic. So we come down to finally here, verify whether we can use the normal approximation. Well, are each of our samples greater than 20? So close your eyes if you get motion sick. I'm going back up. Let's see. Let's look back up here at our sample. Are all of our samples at least 20? Yeah, Ornish is just 20, so it's a little bit tight. Let's see if any of them are extremely skewed. No, they're all pretty evenly distributed. Ornish is a bit, it looks like it may be a bit, but it's not bad. So the largest standard deviation is 9.29 and the smallest is 5.39. So remember, there's 2 things that we have to look at. So let's go back down, close your eyes. Where am I? Okay. So 1, the sample sizes are large enough they're all greater than or equal to 20. And remember, this is also really critical. The largest standard deviation, which is 9.29, is not more than 2 times the smallest standard deviation, which is 2 times 5.39, which is, greater than 9.29. So 9.29 is less than 2 times the smallest standard deviation. So we can use this for the analysis of variance test and for the weight loss, diet and weight loss study. So we're going to end this here. Tomorrow is a lab where you get to work with data and use these ideas more. Remember, this is a little bit different because we have different tests to use. The tests that you'll want to use will be listed in the notes. Follow along and give the lab a try. Hope you have a good day.